Okay, the last time we looked, we were doing a warm up, and the warm up was about this question here. I guess I'll go back to the warm up and show you that for a second. The warm up was about this question here, and it says to self grade it. Well, you're going to self grade it using this video, and the answers are provided here. You're going to answer the front page, and then on the back page, we're going to talk about impulse graphs and about inelastic versus elastic proofs. And so take a look at this and make sure you know what you're doing. So here we go. Excuse me. Okay, so the reason I'm asking you to do this, where you're gonna answer it using only conservation of energy, and then using both conservation of energy and momentum, is that many students try to answer this question using conservation of energy, which is a really smart way to do it. It's a really easy way to do it. And you will get an answer. You'll say, you know, mgh equals 1/2 mv squared, and that will give you the velocity of this object here. And then when they hit each other, now the mass increases, and so now we say this 1/2 mv squared is going to turn out into the 1/2 m plus m times v squared, and you're going to find a velocity. The thing is that final velocity turns out to be bigger than what it should be. And the reason it's bigger than what it should be is because these two items are sticking together. So by definition, energy is not conserved beginning to end. If energy was conserved, then that would work. But the only way that works is if it's a truly elastic collision, where most collisions are not. Most collisions, even when they bounce, are inelastic. So we'll talk about proving this later on. So when you do this, a couple things you want to ask yourself is momentum conserved during time frame 1? And the answer here. And is momentum conserved during time frame 2? So I'm going to kind of go through these questions real quick and not answer the question for you. So is momentum conserved? Momentum conserved, not energy, but is momentum conserved when it's going down the hill? And then when it's a collision with a two-block system with no friction, is momentum conserved? And then it says, is energy conserved during time frame 1? Well, we got a block at the top of the hill. It's going down the hill in time frame 1. Is energy conserved? And once again, no friction on the hill. Is energy conserved during time frame 2? So time frame 2, it's a collision, and they stick together. So you can think about that. Then I get more specific. Are there any outside forces in time frame 1? So looking at time frame 1, are there any outside forces? And then time frame 2, same question. Are there any outside forces in time frame 2 when we're talking about the collision on a frictionless flat incline? And then finally, the last couple things here are during time frame 2 only, is momentum conserved? So just really looking at this, is momentum conserved? And during time frame 2, is kinetic energy conserved? And can you prove it? So the first question is momentum conserved during time frame 1 and time frame 2? So time frame 2, we have no friction. We have a two-block system in a collision. That's kind of the definition of a collision where momentum is conserved. In time frame 1, that's not a collision. It's falling, and the momentum of the object at the top is 0, and the momentum when it's at the bottom is non-zero. So we must have some sort of an impulse going on there, some outside forces acting on this. In this case, it's gravity, because gravity is not included in my two-block system. Is energy conserved in time frame 1 and time frame 2? Yes, energy is conserved. It goes from the top to the bottom. Energy is conserved. It goes from gravitational to kinetic. That's fine. Is energy conserved in the two-block system when it collides? And you should hopefully know that if it sticks together, it is going to be inelastic. Inelastic means energy is not conserved, really. But the perfectly inelastic is when they collide and they stick together, and then we know for sure it's not going to be energy conserved. Energy going to be lost. Is momentum and kinetic energy conserved during time frame 2? Well, once again, I already said this, but momentum is conserved because it's flat and there's no friction, and it's a two-block system. Energy is not conserved because they stick, and it is by definition inelastic. I may ask you to prove It's inelastic though, so be careful about that. Make sure you know how to prove it's inelastic. Okay, and then what do outside forces cause? And can you interpret or draw and interpret FT graphs? So outside forces are going to cause a change of momentum, right? So is there a change of momentum? Is there in the first section? Yes. Is there a change of momentum in the section? No. So is there an impulse in the first section? Yeah. Gravity is a force, and that force is going to act over the time it goes down the hill, and so that's an impulse. On the second section, there is no impulse. Okay, so let's talk about the impulse first. I don't want to tell you exactly what's going on in this scenario, um, because I want to make sure you can do that on your own. But I'll give you an example of a scenario. So we have an FT graph here, and the example is I'm going to push a gas pedal down on a go-kart, and it's shown in the graph over here, which says it's 160 newtons, and it does so for a time of 5 seconds. And so I start here, I push on the gas pedal, and it begins to accelerate over this time of 5 seconds, 160 newtons. And it says, show your equations, use substitution and solution. And the cart has a mass of 100 kilograms. And of course, it says below, I push for 5 seconds. And so that's what we want to know is we want to know how fast it's going to go after the time period of 5 seconds. And so this is VF equals, and the answer is under here, which I'll pop up in a moment, I guess. So let's go back to the front real quick. If you do these correctly on these cases, your answer should be this. And this doesn't make any sense to you right now, but I'm going to X this one out. This is not good. And I'm going to put a check mark here. And that is good. And so on the back side, if that makes sense to you, great. If it doesn't, then let's talk about on the back side. Okay. Just kind of showing you that answer. I guess it's not really related to this answer, so I didn't really have to do that. I could have done it at a different time. Anyways, I think you can do this on your own. So I'm just going to show you the answer just so you can verify. So if you get 4 meters per second as your final velocity, you show your equation, you show your substitution, you show your units, and you know how it relates to this, then you're doing a good job. Okay. So anyways, I'm going to move on to the last section. And the last section is talking about energy and energy before the collision and after the collision. So if we look at this, energy before the collision, it comes from our derivation from speed, which is coming from gravitational potential energy, which you've done this before. And so it actually derives pretty simply. You got to show it on the test. You can't just like, whoop, you got to show this happens. And you should get a velocity of 6.26 meters per second before it hits the other block. So it's at the bottom of the hill. It's going on the flat surface now. It hasn't hit in the other block yet, but it should have a speed of 6.26. So I get the kinetic energy by saying the kinetic energy is going to be equal to 1/2 times the mass of 2 times 6.26 squared, and I'm going to get 39.19 joules of energy. And so then after the collision, if I've done it correctly or incorrectly, it really depends. So this is the correct answer, 4.17, which I solved on the other side. That's what I was referring to when I talked about the other side. And I showed you the two answers. This is the correct answer, right? 4.17, because I'm using the momentum model. So this is the momentum going in with a mass of 6.26, going in with that momentum. Sorry, a mass of 2 and a velocity of 6.26. And then I go in and the masses combine, and I look for my final velocity. I get that. That's on the previous page. And then I do my energy. I'm going to pause this for a moment because somebody wants to talk to me. So hold on one second. Okay, and I'm back, hopefully. Okay, so maybe I didn't leave my spot here. So you found 4.17 was the velocity using the combination of the 6.26 and into the momentum method. Okay, how much energy is that? Well, that's easy because it's the two of them together, which is 3 kilograms, right? 2 plus 1 is 3. And so when we do this, we get 26.08. And if you look back over here, that's less. And that makes sense, right? It's an inelastic collision. So it makes sense. It's lower. If it was a perfectly elastic collision, then you'd have the same amount of energy. So now, um, is that true? So if you would this way, we use the 5.11 instead, right? That was the one that we said was not correct. Now that's using just the energy model. And why not? Well, if you use 5.11 and we think about this, we have 1 half times 3, just like before, but we have a different speed now, 5.11 squared, and you get 39.19, which is pretty much 39.2, which is pretty much the same thing as this, exactly the same. So why is that not possible? Is there ever a case where it would be possible, right? So what you've got to do is you've really got to consider um, what is the difference in the definition of elastic versus inelastic collisions, right? So momentum is always conserved in collisions where there's no outside forces. So that's the first thing you got to consider. If it's perfectly elastic, right, 100% of the energy is conserved, not the energy. The translational kinetic energy is conserved. So your energy at the beginning of motion will be the same as the energy of motion at the end. But if it's inelastic, you have kind of two scenarios. You have perfectly inelastic where they actually stick together when they collide, and we know for sure that's not elastic. It doesn't mean there's no energy. It just we know for sure it's not going to be elastic. If they bounce off of each other, there's only really one way to figure out if they're elastic or inelastic. A lot of people think, oh, it bounces, it bounces, it's elastic, and that's actually not quite true. It could be, right? But it might not. So you got to compare the beginning, which was the beginning energy, to the ending energy. And in this case, that is not possible because they sit together. So hopefully that's enough information that you feel really solid going into the FRQ tomorrow. So let me know if you have any questions, and I will see you on test day.